This is the second video for Chapter 1, covering sections 1.2, 1.3, and 1.4. Section 1.2 talks about observational studies versus designed experiments. The only objective we're going to talk about in this section is to distinguish between an observational study and an experiment. So first we have to define some terminology. An explanatory variable is one which may be used to explain or predict changes in the values of another variable. It's often called an independent variable or a predictor variable. In other words, this is the variable that if we were doing an experiment we might try to change and then see what the effect is on other variables. So a response variable is one for which the values change in response to changes in another variable. This is often called a dependent variable. An observational study measures the value of the response variable without attempting to influence the value of either the response or the explanatory variables. In other words, in an observational study, the researcher simply observes the behavior of the individuals in the study without trying to influence the outcome of the study. If a researcher assigns the individuals in a study to a certain group, intentionally changes the value of the explanatory variable for the different groups, and then records the value of the response variable for each group, then the researcher is conducting a designed experiment. So the real difference between an observational study and a designed experiment is that in an observational study, researchers are just making observations without trying to influence the outcome. In a designed experiment, the researcher is trying to find out something by actually changing explanatory variable for different groups or different individuals. Here's an example. Some researchers wanted to investigate cancer risk among Danish cellular phone users who were followed for up to 21 years. To do this, they kept track of over 420,000 people whose first cellular telephone subscription was between 1982 and 1995. In 2002, they recorded the number of people out of all of these who had a brain tumor and compared the rate of brain tumors in this group to the rate of brain tumors in the general population. Our first question here is, was this an observational study or an experiment? In other words, did the researchers try to apply a treatment or apply something that would change the explanatory variable? No, they didn't. All they did was make observations. Notice here it says they just kept track of these people who had their first subscription between 1982 and 1995, and then they recorded how many of them had a brain tumor. So all they were doing was observing. That would make this an observational study. The next two questions we want to answer are, what would the explanatory variable and the response variable be? Well, the explanatory variable would be their amount of cell phone use. The response variable would be whether they ended up with a brain tumor or not. Another example along these same lines, this is still talking about cell phone use and brain tumors. But in this case, the researchers used rats. So the rats in group 1 were exposed to one level of cell phone, one level of radio frequency radiation. The rats in another group were exposed to a different level of radiation, and the rats in the third group received no radiation at all. The rats in all three groups were treated the same except for the radio frequency. So was this an observational study or an experiment? In this case, we had the three groups, and the explanatory variable was varied according to which group the rat was in. So this would be an experiment. So in both of these studies, the goal was to determine if radio frequencies from cell phones increase the risk of contracting brain tumors. In both of them, whether or not brain cancer was contracted is the response variable, and the level of cell phone usage was the explanatory variable. So often in research, we want to determine how varying the amount of an explanatory variable affects the value of a response variable. Now, a lurking variable is an explanatory variable that was not considered in a study, but that can affect the value of the response variable in the study. Lurking variables are usually related to explanatory variables considered in the study. Here are some more examples. In each of these, we're going to determine whether the study is an observational study or an experiment, and we'll identify the explanatory variable and the response variable. So in this first one, researchers wanted to assess the long-term psychological effects on children evacuated during World War II. They obtained a sample of 169 former evacuees and a control group of 43 people who were children during the war but were not evacuated. The subjects' mental states were evaluated using questionnaires. It was determined that the psychological well-being of the individuals was as adversely affected by evacuation. So, was this an observational study or an experiment? All the researchers did in this case was collect data and make observations. So this would be an observational study. The explanatory variable would be whether the person was evacuated or not. And the response variable would be the psychological well-being. Another example, xylitol has proven effective in preventing dental caries or cavities when included in food or gum. A total of 75 Peruvian children were given milk with and without xylitol and were asked to evaluate the taste of each. Overall, the children preferred the milk flavored with xylitol. This would be a designed experiment because the researchers were actually intentionally changing the values of the explanatory variable instead of just observing. So the children were given a type of treatment. The explanatory variable here would be whether the milk had xylitol or not. And the response variable would be the evaluation of the taste. So whether the child liked the milk with the xylitol or not. The third section in this chapter is about simple random sampling. There's only one objective here, and that is to obtain a simple random sample. So first we can talk about just random sampling. This is a process of using chance to select individuals from a population to be included in the sample. So with a random sample, we select members of the population in a way so that each individual member has an equal chance of being selected. A simple random sample is a little bit more complicated. because for this, we still want to have each individual member having an equal chance of being selected, but we also have to do this in a way so that every possible sample of size n has the same chance of being chosen. So whatever size we want our sample to be, say we want it to be size 10, we have to do this so that every possible sample of size 10 has the same chance of being chosen. Here's an example. Suppose we need to select a simple random sample of size 30 from the children who attend a particular elementary school, which has grades K through 5. To get a simple random sample, basically there can't be any organized method of selection. It has to be completely random. In this example, we could use a random number generator to select 30 names from the list of all students at the school, or another way to get a simple random sample is to put all the students' names into a box and draw out 30 names. The next section talks about other effective sampling methods. So the objectives in this section are 1, to obtain a stratified sample, 2, to obtain a systematic sample, 3, to obtain a cluster sample, and 4, to identify a convenience sample. So first we want to obtain a stratified sample. Stratified sampling means that we subdivide our population into at least 2 different subgroups, usually more, that share the same characteristics, and then we draw a sample from each subgroup. For example, we might divide into women and men, and then select randomly a certain number from the group of women and a certain number from the group of men. Another example, if we go back to our elementary school, to get a stratified sample of size 30, we could divide the students into groups by grade, so 5th grade, 4th grade, and so on down to kindergarten, and then randomly select 5 students from each grade. The next type of sample is a systematic sample, and this means that we have a list of the population, and we just go through and select every kth one. For example, in this picture, we'd be selecting every 3rd individual from the population. If we were going to do this in our elementary school example, to get a systematic sample of size 30 from a population of 400 children, we need to select every 13th name on the list of children. We get 13 because if we divide our total population, 400, that gives us 13.3. So we'd round that down to 13. Now our starting point would need to be some randomly selected name on the list, somewhere between number 1 and number 13 on the list. So we'd select our starting point. That would be our first individual for our sample, and then after that we'd take every 13th name on the list. The third objective is to obtain a cluster sample. Cluster samples are easy to confuse with stratified samples because here we also divide the population into groups. We call these clusters. The difference between this and a stratified sample is that once we divide into groups, then we randomly select some of those groups and we take all of the members of those groups to be in our sample. Here's an example. If we had a state divided up into precincts and we wanted a cluster sample of the voters, then we would randomly select, in this case, 3 of the precincts, and we'd interview all of the voters in those 3 precincts. If we were doing a stratified sample, we would take a certain number of voters from each different precinct. That would be the difference. Here's another example. Back to our elementary school. If we go in at lunchtime and divide the students into groups by which lunch table they're at, assuming each table seats 10 children, then we could randomly select 3 of those tables and choose all of the students from those 3 tables. That would get us a sample of size 30. It would be a cluster sample because we're randomly selecting the groups and then selecting all of the students from those groups. Our last objective here is to identify a convenience sample. Convenience sampling means that we just use results that are easy to get. And you actually see this a lot. This would be things like the newspaper reporter who stands on the corner and interviews the first 10 people that walk by. Now, convenience sampling is not a statistically valid sampling method. If you see this, sometimes the results are interesting, but they're not statistically valid. Here's a summary of our sampling methods. We have simple random, stratified, systematic, cluster, and convenience. If you're trying to identify whether something is a simple random sample, if the sampling method gives you a random sample and you can't identify it as systematic, convenience, stratified, or cluster, then it's simple random sampling. Again, simple random sampling means there's basically no organization to how the sample is selected.